Good morning. Resume the recording. So, just today I have uploaded the new lecture over here. So this is the recorded lecture. So last time the last part of this contract construction was the recorded lecture, and then for the new topic, which is the lecture on topic number 5, construction safety. This is also the recorded lecture. So this is the recorded video on topic 5. The topic is construction safety and health and equipment maintenance. So can you see this screen?
Yes.
Okay, so yes, so I have just selected this lecture and then it is uploading it. Maybe my internet is weak today. No, not, yeah, it's okay, it's working now. So this is the of the textbook. Yeah, this is the topic which I have recorded. Discuss, okay, and then you can have a look. So it is about 1 hour 8 minutes long. Maintenance. Can you see it on the screen now? So importance of safety. And compared with the hired workforce, construction. But anyway, this is for you to accident and facilities and fatalities. It means, yeah, this is for you to see it later, okay, on the YouTube. Okay, and so with this, then you will do it by watching, and then later on, maybe if you have any questions, then we can have the question and answer session for this topic. And its slides are also available. Okay, slides are also available. And yeah, just in the last lecture, I just had the some numerical problems. Okay, it was like a tutorial for the numerical problems. Okay, that was in the last class. And I have also there should be a quizzes. There was a practice quiz. Yeah, so there is a practice quiz as well. Okay. So this quiz is about the time value of money problem. So, so you can attempt that quiz. So for example, this quiz have a few questions, and then you will need to answer those questions. So this can use the, you can read this problem statement, and then you can write your answer over here. Okay. For example, whatever the answer. So you'll write it in the numbers, and then you can attempt it. So practice quiz is important because similar questions will be there in the in your second assignment and also in your midterm exam, which I'm going to take after the break. So you can try those practice quizzes. There is only one at this moment, but I am going to prepare it and put some more practice quizzes. Okay, so do you have any questions up to now?
No, no questions. Okay.
So with that in mind, then I think I can start the new topic. This topic now is a new topic, topic number 6. So up to now, I have covered 5 topics. Okay, let me show you on the course specification form. So where we are now, course specification document. Okay, so in the course specification document, you have the list of topics over here. So we have covered the introduction to construction industry, which was the very first topic. We have covered the planning and scheduling, which was the second topic. In that, we have also that resource assignment and linear scheduling planning. So these 2 topics we have covered: planning and scheduling, resource assignment. And then there was a topic, construction economics. Okay, equipment cost, rental, lease, buy decisions, financial management part, time value of money concept. So, and then this was topic number 4, contract management. This one we also covered. And the last one, which I just said, showed that construction safety, health, and equipment management. So these topics we have covered. So these were the 5 topics. Okay, 5 topics which were related to the construction management part. Now we are moving toward the construction technology part. Okay, so in that construction technology, there will be the first topic, earth moving materials and operations. So that we are going to start now. So since we are in the week 7, so yeah, so this shows that we are almost on the schedule. So there is only change that I have moved this midterm exam from week 7 to week 8. So otherwise there is no much change. So we are going on the schedule. Okay, so it's because just I have recorded this lecture, construction safety, health, and equipment, which you can watch at your own convenience anytime. Okay, so construction safety, health, and earth moving materials and operations. So we can start this topic today. Earth. So this topic is topic 6. Can you see this PowerPoint?
Yes, we can.
Okay. Yeah, this PowerPoint or the slides are still not available on Moodle. I will upload after the lecture. So as of now, you can only watch it on the screen, and as I will be speaking live. So as I said, that this is the first topic of this construction technology part. Okay, construction technology part. Construction management parts topic we have already covered. So your midterm exam will be from those topics which I have covered in the construction management part. Okay, so that means topic 5. So this topic, topic 6, will not be included into your midterm exam. Of course, I will also clarify it through an email to you later on as well. Okay, so this is topic 6 of this course, and then I think this is probably the chapter number 2 of the textbook. I will add this chapter number also in these slides later on. So this is about the earth moving materials and operations. Okay, so earth moving materials and operations. So earth moving materials and operations. So what do we have in this topic? So the first of all, introduction to earth moving. So what are these earth moving operations? So in every civil engineering projects, earth moving operations play a very pivotal role, because all you know that the civil engineering structures are constructed on the ground, and the ground surface is not uh, as desired as we want. So we want to prepare the ground surface to their desired level and characteristics. So the earth moving processes is the process of moving soil or rock from one location to another location and processing it so that it meets construction requirements of the location, elevation, density, moisture content, and so on. So therefore, earth moving operation is not just the moving the soil from one location to another location and for no reason. I mean, there is a reason for moving the earth from one location to another location because we need to prepare the site for the construction work to be performed. And of course, not the soil should be of the desired density. If the soil should be for the desired density, then we will be able to strengthen the soil to our desired level, so that the soil will have the enough bearing capacity to withstand the loads of the construction. So the activities involved in this process include excavating, loading, hauling, placing, that means dumping and spreading, compacting, grading, and finishing. So excavating means, so that means you are digging the soil, you are removing the soil, and then you are loading it into the dump trucks. Hauling means you are transporting it from one location to another location, and then you are placing it, that means dumping it and spreading it on the desired location. And then after that, there will be a compaction, and then there will be a grading, and then finishing. So in fact, in various topics in the construction technology part, we will cover all of these aspects. Okay. So in this topic, I think we will be covering mainly the excavation part or before the excavation part. Okay. Excavation part will come later. So efficient management of the earth moving process requires accurate estimating of work quantities and job conditions, a proper selection of equipment, and competent job management. So all of these requirements are quite straightforward to understand. We need to estimate the work quantities. So that means later on we will see that how we are going to estimate the work quantities in those situations, and then what are the factors which are involved in those, which affect the estimation of the work quantities, and proper selection of the materials. Earthworks are huge works. So therefore, proper equipment with the adequate capacity for the equipment which can dig the earth surface at the desired level, that type of equipment may be needed. And of course, a competent job management using the principles of the project management and proper job allocations needs to be provided. Okay, so the equipment selection. So the first criteria in the equipment selection is the ability of the equipment to perform the required work. So the equipment, whatever the equipment we will choose for that process, should be able to perform that work. Then that equipment should be selected, which should be maximizing the profit or return on investment produced by the equipment. So the selection of the equipment should be based on the quantity of the work performed. So if the quantity of the work is less and we have chosen the very large capacity equipment, that is also not good. But if the quantity of the work is more, and then if you have chosen the small capacity equipment, that is also not good. In both situations, we will not be able to achieve our objectives. So In the first case, when we have chosen a very high capacity of the equipment, then that type of work may be very inconvenient, and on the other hand, it will be also quite uneconomical as well. And in the second case, when the capacity of the equipment chosen is too less compared with the quantum of the work, then will not be able to complete the work in time. So that will also, in another case, indirectly, it will be an uneconomical situation. So the other factors that should be considered when selecting equipment for a project include possible future use of the equipment, its availability, the availability of parts and services, and the effect of equipment downtime on other construction equipment and operations. So uh, remember that if we have already considered the situations when we are going to buy the equipment and when we are going to lease, or when we are going to rent out the equipment. So a general principle which we learned from this construction management topic was that we can buy the equipment if we are going to use the equipment uh, for a appreciably longer period of time. So then buying that equipment may be uh, a better choice. But if we only need the equipment for a short period of time, for a smaller project, then it may be better that you just rent that equipment. Okay. So, and the leasing option comes in between renting and buying. So the same principle can be applied over here. Okay. So what are its needs? What's the availability? And on the other hand, the availability of the parts and services. So this type availability of the parts and services we have also discussed in our last topic, which I recorded it in the equipment maintenance chapter as well. So after the equipment has been selected for a project, a plan must be developed to efficiently utilize the equipment. So we have our master plan for the project based on the project activities. So that master plan of the project that is based on the critical path method, we can use that plan to also schedule the equipment. That means we can, in that plan, we can resource load that plan with the help of the equipment. And then our software, using our software, for example, Microsoft Project or Primavera P6, we can create the resource schedule that will be based on each type of schedule. And then, of course, that schedule includes the equipment plan as well. The final phase of the process is, of course, competent job management to assure compliance with the operating plan and to make adjustments to the unexpected conditions. So the competent job management is the responsibility of the ultimate responsibility is for the project manager, and then more day-to-day or the site level responsibility is for the job supervisor or the construction superintendent who is supervising the job on the site. So they can take the decisions on the site on daily basis, so that they can, considering the overall plan for the utilization of the equipment on the site, they can readjust those plans on the local site locality basis to meet the requirements for the job. Okay, so that was about the equipment selection. So now we can talk about some of the equations which we can use in this topic. What we want to know is that if we want to use such an equipment for the earth moving operation, then what we can do is we need to find the production rate for the earth moving equipment. Okay. We want to know the production rate of the earth moving equipment. So the production rate can be determined by a basic formula. The basic relationship for estimating the production of all earth moving equipment is as follows. So if we say that if we describe this formula in words, it is that production is equal to volume per cycle multiplied by cycles per hour. So this is the basic formula which I think we will be using quite often. So that will give us the production. So for example, if the volume per cycle is in cubic meter, that means in one cycle of operation, we can perform this much cubic meter of the work. And if that machine can produce this many cycles per hour, and then that will be the multiplication of those two terms will be the cycles per hour. So for example, if a machine can, if an excavator can dig 1.2 cubic meter per cycle, and that excavator can have 30 cycles per hour. So 1.2 multiplied by 30, so that will be the production. So I'm taking some random numbers, okay? Like if the volume per cycle is say 1.2 cubic meter per cycle, okay, 1 per cubic meter per cycle, and the excavator can have 30 cycles per hour. That means 30 times it can excavate 1.2 cubic meter. Okay, so if that excavator can, so then the production will be 1.2 times 30. That is what is 1.2 times 30 is equal to? Can you do the maths for me? Hmm?
36.
36. So 36 cubic meter. Yeah. So the production is 36 cubic meter. Okay, 36 cubic meter. And what will be the units for this production? 36 cubic meter per. What will be the unit of production? Yeah, can you just tell by you looking at these units, can you tell me the unit of production?
Per hour.
Yeah, 36 cubic meter per hour, okay, per hour. So, so that means the production will be 36 cubic meter per hour. Okay, so another formula which we can use is that, which is the cost per unit of production. Cost per unit of production. That means dollar per unit, okay? Dollar per unit. So this is the equipment cost per hour. That is equipment cost. So we can rent, if we can rent that equipment, say at $100 per hour, 100. Yeah, if we can rent that equipment for $100 per hour. If we can rent that equipment, say $100 per hour, and the equipment per production per hour is 36 cubic meter per hour, okay? So it is say 36 cubic meter per hour. So per hour will cancel. So it will be dollar per cubic meter, okay? So cost per unit of production. So in the unit of production over here is, in the unit of production is in cubic meter. So that means our answer will be in terms of the dollar per cubic meter. That means our answer will be in terms of the dollar per cubic meter. So 100 divided by 36, 100 divided by 36 is, I don't know, it will be about 2 point something, right? 2.8 something, okay? Cubic meter. No, dollars per cubic meter, okay? So it will be dollars per cubic. Dollar per cubic meter. Okay. So if you divide 100 by 36, it will be, I think, very nearly 2.9 probably. Okay. And you can just see that. So this is the cost per unit of production. Okay. So basic formula we can use. So if we have that machinery, so then we can perform regarding the earth moving operations, such kinds of calculations. Okay. However, these calculations will be affected by the job conditions. Okay, job conditions. So we can use, we can refer to this table. Okay, for this for the job conditions. These job conditions are related with the job efficiency factors for earth moving operations. Okay, and these job efficiency factors from the earth moving operations have been taken from the from this reference. Okay, so this may include identifying the job conditions, excellent, good, fair to poor. If the job conditions are excellent, good, fair and conditions, or on the other hand, we can also identify the management conditions are excellent, good, fair and poor. So based on this, we can take the job efficiency factors. Like, for example, if we identify that the job conditions are good and the management conditions are also good, so we can take an efficiency factor of 0.75. So that where will we place that efficiency factor? So this efficiency factor we will place over here. So if the efficiency factor is say 0.75, so whatever the cost per unit of not the cost per unit, whatever will be the equipment production over here, so we can multiply it with the efficiency factor. So for example, if the equipment production was 36 over here cubic meter per hour, so we can multiply this by the efficiency factors over here. So in this case, then the cost per unit of production will become like this: $100 equipment cost per hour. Okay, that is the that we can calculate from the equipment owning and operating cost, or for the case of rental equipment, the rental cost, then divided by the production. The production in this case will be 36 times the 0.75. That means job efficiency factor will say that the production will decrease by as a proportion of the job efficiency factor. Okay, as a proportion of the job efficiency factor, the equipment production will decrease. So in this case, then the cost per unit of the production will, of course, increase. Okay, if we consider the job efficiency factors. So for the estimation of the job efficiency factors, so we can use these tables. And how we can determine the job conditions and the management conditions. So for the management conditions, we can see these criteria. So for example, skill, training and motivation of the workers, selection, operation and maintenance of the equipment, planning, job, layout, super. So we can subjectively rate the performance of the management conditions. And similarly, we can subjectively rate the performance of the job conditions, or the physical conditions of the job that affect the production rate. So topography and the work dimensions, surface and weather conditions, special. So based on the job conditions and the management conditions, which we can subjectively judge, so we can say that the job conditions are, say, fair to good to excellent to poor. And similarly, we can say that the management conditions will be poor to fair to good to excellent. So we will have some subjective judgment of the job conditions and the management conditions. Based on the subjective judgment, we can then choose the job efficiency factor. And that job efficiency factor we can then multiply with the production rate to find the adjusted production. And that adjusted production can be used in the to find the unit cost of production. Okay, so in this way we can make use of these formulae and the data. Okay, so with this production rate, so now let's talk about the some of the characteristics of the earth moving materials. So, well, in the earth moving materials, the material is the soil and the rock itself. Okay, so soil and rock are the materials that make up the crust of the earth and are therefore the materials of the interest to the constructor. Okay, do you have any questions about this production rate and the job efficiency factors up to now? Okay, so now we are talking about the earth moving materials. So the main earth moving materials we from our in civil engineering perspective are the soil and the rock. Okay, so some materials will be the soil, some will be the rock. So soil, we can see that we can say that the soils are those which are relatively softer materials. Rock are the hard materials. So this is a layman's definition of the soil and the rock. Okay, so general soil characteristics are trafficability. It is the ability of a soil to support the weight of the vehicles under repeated traffic. So on a construction site, heavy machinery, heavy trucks will be passing by on a routine basis. So the soil on the construction should be able to withstand the loads of those heavy machinery. So that ability is called as the traffic ability. Okay. Load ability is a measure of the difficulty in excavating and loading a soil. Okay, so this is the ability. Okay, so that means how easily we can excavate and load the soil. So different types of soil will have different types of loadability, and different types of soil, will have a different type of trafficability. So for example, if the soil is sandy clay, then that may be a good soil from the trafficability point of view, because it can provide enough support for the soil for the trucks to pass by. But if the soil is mostly sandy, then it will be very difficult for the trucks to move from one place to another place. Similarly, from the loadability point of view, loose granular soils are highly loadable. Okay, but whereas the compacted cohesive soils and rocks have low loadability. So loose granular soils, it is very easy. That means you will apply the excavator, and that excavator bucket can be filled very easily. But for the compacted cohesive soils, like clay soils, it will need more force and effort of the excavator to excavate it, and the bucket of the excavator may not be also be completely filled in one go. So therefore, those types of soils will have the low loadability. Okay, trafficability and loadability. Okay. Then I think further we need to consider a few more characteristics of the soil. Unit soil weight is normally expressed in pounds per cubic yard or kilograms per cubic meter. So that is actually the density of the soil. So unit weight depends on the soil type, moisture content, and the degree of compaction. Okay, so based depending on the moisture content of the soil, the unit weight of the soil may also decrease or increase. For a specific soil, there is a relationship between the soil's unit weight and its bearing capacity. So generally, more is the unit weight of the soil, more will be the bearing capacity of the soil. So thus the soil unit weight is commonly used as a measure of compaction. In their natural state, all soils contain some moisture. So the moisture content of the soil is expressed as a percentage that represents the weight of the water in the soil divided by the dry weight of the soil. So this type of formula you may have also learned in your soil mechanics or geotechnical engineering course as well. Moisture content of the soil is equal to the moist weight, that is the weight of the wet soil, minus the weight of the dry soil. So that will give us the weight of the water in the soil. The weight of the water in the soil divided by the dry weight of the soil, that will give us the, and multiply by 100, that will give us the moisture content of the soil in moisture content of the soil. So for example, if we take the sample of the soil, if we take the sample of the soil, and the sample of the soil weighs 502 gram, okay, 502 gram, okay. And if you take the sample of the soil weighs 502 gram, and you put that sample into the oven at a temperature of nearly 100 degrees centigrade for 24 hours. After 24 hours, you take the sample out and measure the weight. And then you find that the dry weight of the soil is 480 gram, okay? So 480 grams. So we can use this formula now to calculate the moisture content. So 502 minus 480 divided by 480 multiplied by 100. So it will be 22 divided by 480 into 100. So you will get in the percentage terms the moisture content. I don't know, maybe it will be 22 over 400 divided by, yeah, so 22 divided by 480, how many percent we will get?
4.58.
Yeah, 4.58%. Okay, so about 4 points. So that means we can say that that sample had about 4.58% of the moisture content. Okay. Okay, so okay, of course, later on it will be clear that why are we going to calculate the moisture content. The soil is considered to consist of 5 fundamental material types, and that this is your basic knowledge from the soil mechanics. So soils can be classified from the engineering perspective into gravel, sand, silt, clay, and organic material. So, and basically this type of classification is about the is from the perspective of the particles. Okay, so because soil is a particulate material, so it consists of different particles. So gravel is composed of individual particles larger than about 1/4 of an inch or 6 millimeter in diameter, but smaller than 3 inch. So any soil which has about the size of which have particles about the size of between 1/1/4 to 3 inch or 6 to 76 millimeter in diameter. Those particles are called as the those soils are called as the gravel. Of course, if we can have even more than 76 millimeter as well. So, but we are not considering them over here. They are, I think, there's something called as the boulders. Okay, greater than gravel are the boulders or some other terms as well. But over here we are only considering up to 76 millimeter particles. Okay. The rock particles larger than 3 inch in diameter are called as the cobbles or boulders. Of course, yeah, this is just I have shared that. So larger than 60 if they are larger than 76 millimeter, they are called as the cobbles, or even larger are called as the boulders. Sand is a material smaller than gravel, but larger than number 200 sieve opening. So number 200 sieve opening is a designation for the sieve opening with a size of 0.7 millimeter. So the sand is between 0.7 to 6 millimeter particles. Okay, so sand particles are 0.7 to 6 millimeter particles. Smaller than the sand particles are the silt particles. Silt particles pass the number 200 sieve but are larger than 0.002 millimeter. That means silt particles are smaller than 0.7 millimeter. So now you can see that the particle size are becoming very small, but they are still larger than 0.002 millimeter. And then the smallest, most practical uh, uh, particles are the clay. The clay is composed of particles which are less than 0.002 millimeter in diameter. So clay particles are very, very small. Silt particles are still larger than the silt particles, although are smaller, but they are still larger than the clay particles. So based on the size, particle size, we have this kind of classification: clay, silt, sand, gravel, cobbles, boulders, and even large rocks. But the last one, which is the organic soil, this type of classification is not based on the particle size, because these types of soils are quite mixed type of soils. And these soils contain particularly decomposed vegetable matter. That means they are mixed with some vegetable matter. That vegetable matter is not just the vegetable; they can be any plants. Okay, they can be any plants, such as leaves, such as uh, some other thing. So organic soils are also have a few types. One of them is the peat. So peat is a highly organic soil having a fibrous texture. It is normally readily identified by its dark color. It has also the odor or the smell and the spongy feel. So it is generally considered unsuitable for any construction use. So normally for the construction use, we have to, if we find the organic soil, so we have to remove that organic soil from the site, because these types of soils are not very not useful, unsuitable for the construction, because they cannot take the loads. They can decay, and then if we want to place any structure on those um, types of soils, it will be very difficult for those soils to withstand the loads of those soils. Although these soils are good for agriculture, okay, good for growing the plants, good for growing the crops, but they are not good for the civil engineering matters. So for the civil engineering matters, I think the soils of concerns are the clay, silt, sand, and gravel. Okay. So that is the soil classification and identification and the classification. Okay, any questions? Okay, so a further further explanation for the classification of the soils is given in this table. Each of these gravel, sand, silt, and clay can be classified into various categories. So for example, a well-graded gravel. So well-graded gravel will be represented by a symbol GW, where G is for gravel and W is for well. And well-graded gravel will mean that it will be that gravel which will have different size fractions in appropriate proportions. So as you know that the gravel will have a size proportion ranging from 6 millimeter to 76 millimeter. So if we take the further proportions from 6 to say 16 millimeter, from 16 to say 26 millimeter, from 26 to say 36 millimeter. So for each of these proportions, every proportion will be present in almost equal quantity. So that type of soil will be then called as the well-graded gravel. Okay. On the other hand, there will be a poorly graded gravel. So in the poorly graded gravel will be that gravel in which some proportion some proportion of the size will be missing. Okay, so that will be called as the poorly graded gravel. And then similarly for the other silty gravel, and then we have some designations. So that means the gravel, sand, silt, and clay and others, these were the main categories. And so these main categories have been subdivided into certain subcategories. And in this table also shows their properties in the subjective terms, their properties. So for example, the drainage, if we want to use that gravel for some, to provide some drainage of the water, so then it, for the drainage, it will be an excellent soil type. For the construction workability, it will be excellent because it's very easy to load and place. Although the gravels are relatively heavier, but of course, because they are loose materials, so they can be easily placed. Then suitability for a subgrade. That is, a subgrade is a material. Okay, subgrade is the layer for the road construction. That means the layer of the soil for the road construction. So for when a road is constructed, then a layer of soil is made. That layer of soil is called as the subgrade. And then on the subgrade, you place the other materials such as the pavement of the soil. So for the subgrade, it is a very good material. And it is suitable. Its suitability for surfacing is also good because it is a well-graded gravel. And then since almost all types of sizes are available in this well-graded gravel, so then sizes of the gaps due to the bigger particles can be filled with the smaller particles. So for surfacing, it will be a good material. So similarly, then we can see that the properties of the soil vary from excellent to poor, excellent to poor, good to poor, and good to various poor. So that means as we go generally down in this table, the properties of the soil change from good to poor. And what we can say over here is that the gravel has two. Gravel has four classifications. Okay, gravel has four classifications: well-graded gravel and the poorly graded gravel. And then there is a silty gravel. So gravel with the silt particles. So G with M. So M is the symbol used for the silt. G is for the gravel. And then clay gravel, gravel with the clay particles. Okay. So when the gravel is there with the clay particles, its drainage will be poor because clay is a very fine material, and then it will fill up the spaces between the gravel particles. So the drainage will not be poor. But the poor drainage does not mean that it is a bad quality. The drainage property depends where we need the drainage and where we don't need the drainage. So where we need the drainage, then we can provide the materials with the excellent drainage. But where we don't need the drainage, then we can provide the materials with the poor drainage. Okay. So based on the requirements, we can choose the material. So gravel has four types, and then after that sand. Sand has 1, 2, 3, 4, also four types. So sand also is a well-graded sand and the poorly graded sand. So sand also has the excellent drainage properties. Then there is a silty sand and the clay sand. So we have well-graded gravel, well-graded sand. We have the poorly graded gravel, poorly graded sand. We have the silty gravel, we have the silty sand. We have the clay gravel, we have the clay sand. Okay. So these are the 8 classifications of the sand and the gravel. So sand and the gravels are those materials which are the two largest in terms of the particle size. And then start the silt. Okay, so silt is identified in some slightly different manner. So it is ML. It is called as the low plasticity silt. So, and then there is another silt, high plasticity silt, MH. MH is the high plasticity silt. So silt has two types, low plasticity silt and high plasticity silt. So silt and clay compared with the sand and gravel are different in a manner that in the clay, the sand and gravel are the non-plastic soils. That means these are those soils which do not like if you will compress those soils, if you can pull, or you can they do not have a kind of like flexibility. Okay, these type of soils. So we will but the silt and the clays, they have the property which is called as the plasticity. So therefore their classification is based on the low plasticity and the high plasticity. So the silt can be a low plastic silt, but that silt can be also a high plasticity silt. Okay, and similarly, the clay can be a low plasticity clay, and then can be a high plasticity clay. So which is represented by Cl and Ch. And then the other soils which are called as the organic soils. So this is the low plasticity organic soil, OL, and then high plasticity organic OH. And then there is another one which is called as the peat. So for the peat, you can see that everything is unsuitable, poor to fair drainage, construction workability. So peat is that soil which is poor. But on the other hand, there are some high plasticity clay, drainage is poor, construction workability is poor, and the suitability for subgrade is very poor, and then suitability for surfacing is also poor. So in this way, therefore, we have classified the characteristics of the soil, and this is under the unified system of the soil classification. Okay, so we have the 4 types of gravels, 4 types of sand, 2 types of silt, 2 types of clay, 2 types of organic soil, and 1 peat. Okay, so total in this way we have identified, and their properties generally change from excellent to poor as we go down this table. So this, in this way, I have described this table. Do you have any questions about this table? So this was the unified system of the soil classification. Yeah, any questions? Okay, so now let's move ahead. So now let's talk about the soil volume change characteristics. Okay. So what does it mean? Soil volume change. That means the volume of the soil, the change in the volume of the soil. Okay. So remember that the volume of the soil, now here we are talking about a kind of soil, for example, which will have the clay, silt, and sand are mixed. Okay. So if it is a general characteristics that if the soil is dried, if the soil, if there is a moist soil, initially if there is a moist soil and if the soil is dried, the volume of the sand will decrease. The volume of the sand will decrease. So therefore, the change in the volume of the soil is an important characteristic when we are performing the earthwork operations. So for this, we need to understand a few definitions. Okay, so one of these definitions are called as the bank definition. So what is a bank? A bank is a material in its natural state before disturbance. So that means if the soil, if there is a ground which has been there naturally, that means there no human activity has taken place on that ground, and the soil is there on that ground in its natural state. So that is called as the bank conditions. It is called as the bank condition. So it is often referred to as the in place or in situ conditions. Okay. So a unit volume is identified as a bank cubic yard or bank cubic meter, BCY or BCM. So the volume of the soil in the bank condition is called as the bank volume, or if it is measured in the cubic yard or cubic meter, so it is measured in the bank cubic yard or bank cubic meters. Okay. Then there's another condition which is called as the loose condition. So materials that has been excavated or loaded. So that means the soil was in the bank condition, and then we use the excavator or the machine to load that machine into the dump truck. And when we load that machine into the dump truck, then it is not the bank condition. Then it is called as the loose condition. So in this loose condition, we call its volume as the loose cubic yard or loose cubic meter. So there will be a difference between the bank condition and the loose condition. Okay. So generally, when in the bank condition, the volume will be less. In the loose condition, conditions, the volume will be more. There will be an increase in the volume. So in the bank condition, it is in its natural state. It will be in its natural state. It may be compacted state. And when we remove it from the compacted stage, so the stresses along the soil will be removed and the soil will expand into its loose condition. Okay, so that is called as the loose condition of the soil. And then the compacted condition, material after compaction. So it is a unit volume is identified as the compacted cubic yard or the compacted cubic meter. So that means once we have placed, once we have transported that soil to its location where it is placed, and then we are compacting it using the compacting machine. So then it will be in its compacted situation. So then from the loose situation, it goes into the compacted situation. So the loose volume, compacted volume will be then less than the loose volume. Okay, but it may or may not be greater than the bank volume. So so the bank volume, the volume will increase to the loose volume. The loose volume, the volume will decrease to the compacted volume. So these are the bank, loose, and the compacted situation conditions of the soil. Any questions about this? Okay. Now let's talk about another property which is called as the swell percentage. So swell percentage is a soil increase in volume. Okay, when it is excavated, because the soil grains are loosened during the excavation and air fills the void spaces created. So this is what I have just said, that and so in the bank condition, when the soil is soil goes from the bank condition to the loose condition, the volume of the soil increases. As a result, a unit volume of the soil in the bank condition will occupy more than one unit volume after excavation. So this phenomena is called as the swell. So swell may be calculated as follows. So swell percentage is equal to the weight per the bank volume divided by the weight by the loose volume, and then -1, and then multiplied by 100. So this is the percentage of the swell. That means how many percentage of swell has taken place. That means how many percentage the volume has increased. Okay. So if we take the same volume, same weight in both situations, the bank volume will be different. So using this, then we can find the swell in the soil, percentage of the swell. Okay, so this is the example for the swell.
Sorry, Professor, can you please again explain this phenomenon? I mean, so bank condition is when it is not like excavated. Yep.
Yes.
And the soil is not excavated.
Yes. Bank condition is the unexcavated natural condition.
So I did not understand actually how. I mean, can you please re-explain it?
No, explain what I mean. Yeah, but you understand that the bank condition is the natural condition, right?
The swell. I mean, swell.
Yeah.
I cannot
swell.
understand. Yep. How does it happen? What is that?
swell. So swell happens because if the soil is in its natural state, and when you excavate it, so you can see that when the soil is in its natural state, so soil is confined from all sides. Okay, so when you remove the soil from from its natural state and put it into the dump truck, so that confinement has been removed. So when that confinement has been removed, so then the soil then that soil can expand it. The soil can expand. The spaces between the soil particles can be filled with the air, and then that expansion in the soil is called as the swell. So
Yeah,
soil
so,
become
but
loose.
why?
So when the soil
Uh-huh.
becomes loose, so that condition is called as the swell condition. Okay.
So why
So
unit volume
compacted.
of, uh-huh.
Huh?
Why
What?
unit volume of soil in the bank condition is more than after excavation? So if it is if it is
The
increases in volume,
unit weight of the unit weight. Okay. The unit weight of the soil in the bank condition will be more in this the unit weight in the loose condition.
unit weight or unit volume?
No, unit weight. There is
So
nothing as the unit volume. Unit, we're talking about the unit.
no, it is, I mean, it is written here as a result, the unit volume of soil in the bank condition will occupy more than 1 unit volume of excavation.
As a result, a unit volume of soil in the bank condition, right, will occupy more than 1 unit volume after excavation. So this is correct. Yeah, this is correct.
So the volume of the bank condition is higher than the volume after excavation.
Yeah, the volume in the loose condition will be higher than the excavation. Okay.
But
So
it
as
is
a result,
increased. I mean, so I cannot. So I mean, soil increases in volume when it is excavated. Why in the bank condition it is higher?
in the bank, no, you are confusing both things. As a result, a unit volume of soil in the bank condition will occupy more than 1 unit volume after excavation. That means when for example, if the volume of the soil in the bank condition is 1 cubic meter, so the same 1 cubic meter will become, say, like 1.1 cubic meter after the excavation. This is the meaning. Okay?
I got it.
Yeah, maybe I can write it. I think I should be explaining it more over here. So for example, as a result, okay, so when the air fills the voids, so if, for example, a unit volume of the soil in the bank condition, so for example, if it is 1 cubic meter, so that 1 cubic meter will just simply expand to, say, about 1.1 cubic meter. Okay, so that means a 10% volume increase. But remember that for the formula, in the formula, we don't normally in the formula is in the formula we don't normally measure the volumes, because we cannot measure it through the volumes. We can measure it through the unit weights. Okay, so therefore this unit weight in the bank condition, that is the weight per unit volume in the bank condition and the weight per unit volume in the loose condition, should be compared. Okay, so that means you can see that the density, you can measure the density in the bank condition, you can measure the density in the loose condition, and the ratio of that density will be the percentage swell. Okay.
Oh,
So
you got it.
yeah. So it's very simple concept, but just if you got it, then it's very easy. Yeah. Okay, so as an example, you can say that find the swell of a soil that weighs 2,800 pounds per cubic yard, or 1,661 kilogram per cubic meter in its natural state. So that is the bank state. Okay, and 2,000 cubic yard, or 1,186 kilogram per cubic meter after the excavation. So by some methods, we measure the density of the soil in its bank condition, and then after we have excavated it, we measure its density again, and then we can find the swell. So swell will be, in this case, simply it will be 2,800 divided by 2,000, or 1661 divided by 1186. Either if you use the pound per cubic yard units or the kilogram per cubic meter. In this case, we can find that in this case, the soil has swelled 40%. That is, it means that, okay, so that's 40% means that a 1 bank cubic yard of material will expand to 1.4 cubic yards after excavation. This means that if that soil has a swell of, say, 40%, if that soil has a swell of, say, 40%, so it will a 1 cubic meter. If it is in the natural state, so that will become 1.4 cubic meter. Okay, 1.4 cubic meter. So, but in this case, why do we need to consider swell? So we need to consider swell because this will affect our ability to use the equipment. Okay, so for example, if we have later on, if we will have the excavator, if we will have this excavator, so that excavator bucket, or maybe will have some fixed volume, so maybe 1 cubic meter. Okay, so if, for example, on the job site, we have, say, 100 cubic meter in the bank condition, the soil is, so, and its swell is 40%. So it will mean that instead of for this excavator, we need to plan for an excavation of 140 cubic meter. Okay, job. In addition, instead of 100 cubic meter. So that excavator will work for 140 cubic meter of soil compared with the 100 cubic meter of soil, which is in the bank condition, or which is in the natural condition, because the excavator will transport the loose soil. Okay, the excavator will transport the loose soil. So that's why we are considering this swell. Okay, so this is the reason why we are considering this swell, because the production from the excavator will be measured in the loose volume. So we need the loose volume for the production of the excavator, and then we want to find how much loose volume we have to do it. So if we just make our calculations based on the bank volume, then our calculations will be wrong. So therefore, as in this case, we need to consider the swell. So another soil volume change characteristics. Another thing is called as the shrinkage. Okay, so whereas the swell is the increase in the volume, shrinkage is the decrease in the volume. So when a soil is compacted, some of the air is forced out of the soil's void spaces. As a result, the soil will occupy less volume than it did either the bank or loose conditions. So this phenomena, which is the reverse of the swell phenomena, is called as the shrinkage. So the value of the shrinkage may be determined as follows. So similar to the formula for the swell, the shrinkage formula can be the weight per the bank volume divided by the weight by the compacted volume. So that means once the loose soil is compacted, okay, so because then so the swell we can take in those situations, and that means the swell in the previous case, swell we can take in those conditions when we are excavating the soil and transporting it. Whereas the shrinkage we can consider in those situations when we are placing the loose soil into some final place of destination. For example, in the some cut and fill type of calculations. So in when filling the soil, it is at a construction site, then we can consider the shrinkage factor. So if we have a loose soil, we place that soil and then we are compacting that soil with some compactors. So the volume of the soil will decrease and its unit weight will increase. So in this way, then we can calculate the shrinkage. Okay. So swell, not only the swell is considered, but the shrinkage is also considered. Okay. So as you can see over from here is that 1 cubic yard in the natural condition is excavated. So 1 cubic yard in the natural conditions. But now when we put it into the dump truck, when we put it into the dump truck, it becomes 1.2 cubic yards. Suppose if the swell is 25% in this case. But when we place that soil, when we place that 1.25 cubic yards meter soil, we do the compaction. So this is a compactor. When we do the compaction, so this 1 cubic meter original soil now becomes the 0.9 cubic meter soil. So that we compared with the bank condition, the shrinkage is 10% in that soil. So this is the concept of the and the places of application of these swell and shrinkage quantities. Okay, so swell is considered while loading and hauling the material. Shrinkage is considered when we are placing the soil in its final destination for filling purposes and in that situations. Okay, so this is how we put the swell and shrinkage in our calculations. Okay. So that was about the shrinkage. So the example of the shrinkage is that if, for example, find the shrinkage of the soil that weighs 1661 kilogram per cubic meter in its natural state and 2077 kilogram per cubic meter after compaction. So the shrinkage is then 1661 divided by 2007 and 1 minus this, then shrinkage in this case is 20%. So it means that a bank cubic meter of the material will shrink to 0.8 compacted cubic yards as a result of the compaction. So this is just the meaning of the shrinkage and compaction. So remember that swell is also compared with the bank volume, and shrinkage is also compared with the bank volume. So we are not comparing the loose volume and the compacted volume. Okay, so the comparison is always with respect to the bank volume. Okay, so while this is how these two formulas work for the swell and shrinkage. Okay, so that's all for today. Do you have any questions?
Yes, Professor, I have a question.